Hello. So in this episode, we'll together read a paper, and it's in the machine learning or the deep learning field. And we know that game theory is applied to many different fields, and including all those AI or deep learning fields. And today we'll look at this paper called Generative Adversarial Nets. Okay, so basically, the authors they use a minimax game, so they applied the idea of game theory. So a minimax game is sort of a zero sum game with two players. So which are two players are competing to each other, and they applied to this idea to their model, okay, and build this two neural networks to train to build this algorithm to train those two neural networks. So this paper opens or it creates this very new approach, and that is widely used by a lot of other people later. And this model is sort of very famous in a way that it creates a new way of the studying the generative models, right? Because we know that in machine learning or deep learning, there are different kinds of models, right? So one of those is the discriminative model, and it means that the model could estimate the conditional distribution, right, given the data, and it outputs a label. And there is another different class of the model is the generative model. So basically, it measures or it outputs a joint distribution over the input and output, right? So it creates some new data, okay, given some domain. So that's the idea of generative model. So this paper, generative adversarial nets, so they opened or they provided this new approach in the studies for the generative models using this idea of the minimax game by creating this adversarial sort of training algorithm. Okay, so that's the essentially the main idea. And let's see from from an economic perspective. Let's together read this paper and try to understand how game theory is really applied to other fields such as the machine learning or deep learning field. Okay. All right. So and we noticed that this paper is written by a lot of authors, including Goodfellow and Benjio, who are also very famous in their fields. And okay, now let's look at this abstract. So they propose this new framework for estimating the generative models, right, as we just mentioned. And this approach is via a so-called adversarial process. Okay, so it means that there are two models trained simultaneously. So one is called G, it's a generative model. Okay, so that is trying to capture the data distribution, and the other one is called the discriminative model D, that is trying to estimate the probability that the sample is coming from the real training data or is from the G. Okay, so that's what D is doing. Okay, so the training procedure for G is to maximize the probability of D making mistake. Okay, so that's what we call a zero sum game or a minimax two-player game, right? So because in this game they're competing to each other, and the gain of one player is the loss of the other. Okay, so in the space of the functions G and D, and they rigorously showed that there exists a unique solution. Okay, and G is recovering the training data in the equilibrium, and D equals to a half. So this means that in equilibrium, in the convergent equilibrium, then this G, after many iterations or many epochs of training, then this G function or this G model is successfully recovering the training data distribution. Okay, and at that time, because G looks very similar to the real distribution, then D cannot really distinguish G from the real distribution. So it means that D must be equal to a half in equilibrium. Okay. All right, and for simplicity, they used MLPs, so multi-layer perceptrons for G and D. Okay, and so that those are differentiable piecewise linear functions. So the entire system could be trained with back propagation by the differentiabilities, right? And there's no Markov chains or anything else, so the calculations should be pretty simple compared to the previous works of those other generative models. Okay, and they gave some experiment results. Okay, so now let's directly dive into the model. Okay, so to learn this the generator's distribution PG over the data x, this is a variable, this is a vector of random variable. So we define a prior distribution on some noise, who is just random variables. It's also a vector of random variable z. So pz is the prior distribution of z. Good. So and then represent a map to data space as this function. So g takes z as input, and theta g is just the parameters for the MLP of g. Okay. So also define a second MLP called d. So theta d is correspondingly the parameters for d, and x is the vector of the data. Okay. And d outputs a probability that x is coming from the data rather than from PG. Okay. All right. So it means that so D is trying to distinguish whether this data is coming from the real distribution or from the fake distribution. Right. Okay. So the purpose is to train this D to maximize the probability of assigning the correct label to both training or from the fake distribution. Right. To correctly classify those two different distributions, right? And the G is trained to minimize something. So what is this? Let's take a closer look. So if we have a very nice G, which is well trained, so it means that no matter this what random noise is, so this is input into this G. Okay, so then G takes this random noise as the input, then outputs some distribution. Okay, then if this D is good enough to tell that, okay, so this means that because D is maximizing the probability of assigning the correct label, right? So and dx, this function outputs the probability that x come from the data. So it means that if d is good enough, okay, then this should be 1, right? So it means that this whole thing would be log 1 minus would be 0, okay? So log 0 would be minus infinity. Okay, so if that's the case where this D is very good, right? So D could tell this data is from the real distribution or not, right? But if the other case, if D could not tell the difference from those, then it means that given this noise Z and input that into G, okay, then G outputs some distribution, okay. All right, and then if D is not good enough, okay, then let's say some number smaller than 1, right? Let's say in the extreme, let's say if that would be 0, okay. So if that's 0, then 1 minus 0 is 0, right? So 1 minus 0 is 1, so log 1 will be 0, right? So it means that in this case, this is much higher than minus infinity, right? So this means that in this case, so that's why they're saying that we want to train this G to minimize this term, right? So if G is well trained, then this is minimized to a very small number, right? But if G is not well trained, then this could be something pretty big, closer to 0, right? So in that case, D could really distinguish the fake data from the real, right? So that's basically the idea of this model. Okay, now let's have a closer look here. So in other words, D and G, they're playing a two-player minimax game, right? All right, so this is where the game theory comes into the play, right? Okay, and they define a objective function, and they call this as a value function. V takes G and D as the input. Okay, so basically those two things are the two functions, right? And the two functions that are going to be trained, okay, in a very high dimension. Okay, so let's take a look at this definition of this V function. Okay, so it has two parts. So those are two expectations. All right. So the second part is we just mentioned that, right? So we can see the second part is log 1 minus d gz, right? So that's exactly the same we just mentioned. And the first part is that it is just the expectation of the log of dx. So it means that we take this expectation over the log of dx, okay? So in this case, we want to maximize that, okay? So it means that by training this d, okay, if d is predicting or is discriminating very well, okay, then it means that this could be no matter, so this d is giving some number closer to 1, right, as the definition on the previous page. So this term would be 0, okay, so overall it would be 0, all right. So this is just the expectation of over the data x, okay, according to the distribution of the data, okay. And we just showed that the other part, if we maximize over d, then this would be 0 as well, right? If d is doing well, then this would be 0, right? Okay, as we just mentioned in the previous page. But in the meantime, because this is a two-player minimax game, right? So the other player G is trying to minimize this whole thing, right? So because this part doesn't have any G, right? And we will mention the design of this algorithm. So this is not involved into the G part. So the only thing that G, the training of G is affecting is this part, right? So as we just mentioned in the previous page, so by training G, we just want to G wants to minimize this, right? This part. Okay, so this is the definition of this objective function of the two-player minimax game, right? All right, so and we can also take a look at this figure, and this is quite helpful for us to understand how this works, right? So basically, Z is the noise. So in this case, this is a uniform, okay, with a prior of uniform, and and these dotted normal distribution are those are the real data generating distribution, right? Okay, so this green solid line are the distributions that are generated by the G. Okay, so this is simply the X, right? And this is generated by G. Okay. All right, and this blue dashed line here is the D, right? So in the beginning, this G is not working very well. Okay, and G is generating some distribution which is pretty biased and toward to the right, right? And in that case, okay, this D is also not very well, and D, although D could tell something, give some information that in those areas, this D outputs pretty high, relatively high level of the probability that in this area is pretty low, but it has some fluctuations and some and it's not a pretty nice result for D as well, right? So because this is just the beginning stage, okay, and this after some training iterations, then what we are trying to do is to let this G. So before that, okay, before we train G, so the first thing that we need to do is to train this D, okay. So after that, this D is to train sort of better than that, okay. So now in this case, G could stably distinguish in those regions that is different, right? To tell the difference that in those regions that the this outputs a relatively high probability, so that it says that in this region it's the distribution. This is from the real distribution, and the other okay, and the other part outputs a pretty low level of the probability from D, right? And after that, in C, in this part, actually, we can see that those two distributions are coming closer. So this means that we're trying to update this to back propagating to the errors and to update this to train this G. So in this case, then after that, the G is outputting some distributions are pretty closer or looking pretty similar to the data generating process, this dotted black points, right? So the green solid line is closer to the dotted black point. So in this case, okay, then this D, okay, D also improves by itself, and D could only by training better or like by performing better or making more accurate predictions or discriminations, then in this case this D could tell the more subtle differences from the dotted line and the green line, right? So they improve together. And in equilibrium, in convergence, then we can see that this dotted line, this D, is a half. Okay, so it cannot really distinguish from the black dotted line and or the green solid line, right? So they look exactly the same here in this case. And then we can use this G as something well-trained network for us to generate some nice data, right? That looks pretty similar to the real data. Okay, so that's essentially what they're doing by using this model. Okay, now we can briefly take a look at this algorithm. Okay, so this is a mini batch stochastic gradient descent training of the GAN, right? Generative adversarial nets. Okay, so there are a number of steps to apply to the discriminator. So as we just said, so before we train the G, we need to update D first in the beginning of each iteration, right? So at each step of K steps, then we have a we need to sample a mini batch of m noise samples, okay, from the prior of the noise. Then we sample a mini batch of n samples from the data. Okay, good. Then we have 2m together in this mini batch. Then we update this discriminator first by ascending its stochastic gradient. Okay, and basically we just take this gradient over the objective function we just mentioned previously, right? Okay, so after we do that, then this is after k iterations here. Okay, then we could start to train this g, right? Because we already have a nice discriminator now. Then we can start to try to update our g, because the first term doesn't involve any g, so we only update the second term here for the g, right? And using those noises. Okay. All right. And after that, then it goes back all the way to the beginning, right? And the as we just mentioned before, so the D takes the generated picture or the data from the real data distribution and try to discriminate, right? And then we train this D again, okay? And after that, then we train the G. Okay. So that's how this algorithm works, right? And also in the section 4.1, they gave some very nice and rigorous results for the theoretical parts. Okay, and this should be pretty easy for us to understand. And so in the proposition 1, they said given a fixed G, so the optimal D should be something looks like this. Okay, so it's the proportion of P out of P, the P of data out of P data plus PG, okay? And that's simply, that could be proved by just taking the expectation or just expanding the object function, right? And by replacing the expectations with the integrations, and we can see that if we substitute the x, substitute gz by x, then we can combine those two terms together and pull those integrations out, right? And essentially, this could be written as some form using this, right? So it's something times log of something plus b, plus some other constant times log of 1 minus that variable, right? So, and it looks like this. So it means that this function has a maximum because it should be a concave function, right? And its maximum is just given by those parameters, right? And that completes this proof, okay? And also, they said that the training object for D could be interpreted as maximizing the log likelihood for estimating the conditional probability, okay? And the Y indicates whether X come from P data or from PG, okay? So it's either Y is 1 or Y is 0, right? So the minimax gain in the object function could be then reformulated as this, right? Remember this first term and plus the second term. So and we plug in those V we just showed from here, right? Okay, and they gave some other theorem, and we can briefly take a look. So theorem 1 says the global minimum for this C, okay, is achieved. So basically, this is showing some convergent result there, right? So it shows that, okay, well, using this algorithm, we can actually really achieve that equilibrium, sort of the equilibrium, right? Okay, and so it's achieved if and only if PG equals to P data. So, and they proved that Y is that, right? Okay, so if those two are equal, okay, and this is a half, all right, and we find that CG is minus log 4, okay, and basically this proof is using the KL divergence, okay, so and it should be a symmetric case of that, and it's called the Jensen-Shannon divergence, okay, so it'll be so this JS divergence between the two distributions, so it's always non-negative and 0 when they're equal, okay. All right, so we'll just skip this proof and leave this to you if you're interested in this, okay, and this shouldn't be pretty relevant to this algorithm, okay. It's just showing, basically it's essentially showing the showing why this is working, and showing that in the sort of the equilibrium, that what's the condition for that, right, the theoretical result, okay. And also they have this convergence from the theorem 1. If G and D, they have enough capacity, and at each step of algorithm 1, the discriminator is allowed to reach its optimum given G, and PG is updated so as to improve the criterion, okay, of this object function, and then PG converges to P data. So those are just some convergence results, okay. All right, and then after that they showed some experiments using the MNIST or some faces or some animal pictures data to show that its ability to generate some images in data, okay. All right, and of course this works opens a relatively new approach, and it provided a very nice way to actually to study or to create or to generate the data by those generative models, right? So which is quite different from the previous approaches. And of course we just briefly reviewed how it's using game theory to actually help the researchers in computer science to actually create or to develop some sort of like this algorithm 1, to develop those algorithms to help to train those models, to actually those are just probability models, right, to using those games to train the models to help to create the new data, okay, in either in many fields of computer science, such as the images or the text or something else, right. Of course it has advantages and disadvantages, right. So we just mentioned there are a lot of advantages, and of course the disadvantages are such as the convergence or the implementation of the model. There should be some minor problems, but a lot of other people, they're fixing this later, right? And this gives many new possibilities for people to follow this work. Okay, all right. So that would be everything about this paper. And if you're interested, then you can have a look, and this will be a very interesting and inspiring work. Okay.